Hello students, let us do a quick review to in-class exercise 1 for topic 17 carbonyl compounds. For the first question, we have lactic acid, otherwise known as 2-hydroxypropanoic acid. You are given the formula. Based on the formula, you know that there is a chiral carbon right in the middle over here. Okay, then it's present in milk. You were also told that it can be made in the laboratory from ethanol by the following reaction. Okay, so you have step 1, and then you realize that in step 1, the CN is being added, probably across the CO double bond. Just to let everyone know that whenever a formula is written as CH3CHO, CHO represent aldehyde functional groups. Yeah, so please do not write aldehyde as CH3COH. Okay, so this is incorrect. If you want to write an aldehyde out, it should be written as CH3CHO. Okay, so clearly step 1 is a nucleophilic addition step, and then step 2, you realize that the C triple bond N is gone, and then you get a carboxylic acid. Yeah, so step 2 should be acidic hydrolysis, something which you are very familiar with from the topic halogen derivatives onwards. Okay, so for question A, part 1, you are supposed to name the reagents and conditions used and type reaction for step 1. So clearly this is nucleophilic addition. So if it's nucleophilic addition, then we just need to look at our notes. What we need is HCN, okay, with trace amount of KCN as the catalyst. Okay, so the trace amount of KCN provides the cyanide nucleophile, which allows the slow step of the nucleophilic addition to take place before the alkoxide being formed is being used to deprotonate HCN and produce more CN minus. Okay, so the condition will be cold. Okay, so some of you might recognize from the old curriculum that in the old curriculum we need the students to write 5 to 10 degrees Celsius, but this is not required for the current curriculum because we don't need you to remember the exact condition. Okay, another reason why we don't need you to remember the exact condition is because probably for every aldehydes, ketones, the condition will differ slightly. And if you look at your notes carefully, the reason why we need to perform the reaction under cold condition is to ensure that your HCN does not vaporize. Okay, yeah. So A2 is a very straightforward mechanism question. You are required to describe the mechanism for this reaction, and then in your answer you should draw all curly arrows, lone pairs, charges, okay, so etc. Okay, so as per all question, if you remember from the very beginning when we first discussed free radical substitution for alkanes, you need to write down the name of the mechanism. Okay, so the name of the mechanism is nucleophilic addition. Okay, you need to write it out clearly. Okay, so for nucleophilic addition, the first steps involve the nucleophilic attack by the cyanide nucleophile. So this is the slow step. And then there is a need for you to write down the charge separation, delta plus, delta minus. Okay, and then the cyanide nucleophile. Remember that for cyanides, the carbon is the one bearing the negative charge. Okay, and the lone pairs of electrons, which is the nucleophilic source. Okay, so attack the carbonyl carbon, and then the CO pi bond break towards the oxygen. And then in the process, you form this particular alkoxide intermediate. Okay, so O minus. Okay, and then remember to put down your lone pairs of electrons on your O minus, because later on in your fast step, okay, then you can clearly show the deprotonation of HCN. Okay, so the deprotonation of HCN begins from the lone pairs of electrons on the alkoxide attacking the electron deficient hydrogen. Okay, so this is the protonic hydrogen, and then the HC bond will break heterolytically where the carbon will gain the lone pairs and the negative charge. Okay, and then yeah, so this is the nucleophilic addition step. So you have a CNH and then OH plus CN minus. Okay, so it is of vital importance for you to show the regeneration of the cyanide catalyst. Yeah, I think that's about it. Okay, so make sure you understand that the phrasing to the question for mechanism for H2 tends to be always something along the line. You need to show all charges, lone pairs, and the movement of electrons using curly arrows. Yeah. Okay. Then The next part, lactic acid is present in milk, rotates plain polarized light. Lactic acid produced in the laboratory by the reaction above does not rotate plain polarized light. So what feature of lactic acid present in milk causes the rotation of the plane of polarized light? Okay, so that the structure you probably will be aware of is that, I think number one, the lactic acid contains a chiral carbon. So that means it has an asymmetrical carbon bonded to 4 different groups. Okay, then why is it that in milk it can rotate plain polarized light, but in the lab it can't? I mean, in a sense, the lactic acid produced in the lab by the above reaction, so by this particular nucleophilic addition, why is it that it can't rotate plain polarized light? Okay, so for the lactic acid present in milk, we can safely conclude that it contains only one enantiomer. So the lactic acid in milk, okay, contains only one enantiomer out of the 2, of course. Okay, yep. However, the one you produce in the lab using the above method, right, you will notice that in the slow steps, which is this particular step, I'm going to box it up. Okay, so I'm going to showcase to you below. So if we show the stereochemistry of the group, so we have a methyl group projecting in, a carbonyl carbon, and an H projecting out. Okay, so you notice that the carbonyl carbon, right, is trigonal planar about, okay, the carbonyl carbon. Okay, so in terms of geometry, so in that sense, right, your cyanide nucleophile can will then approach it from the top and bottom plane with near equal probability. So this is the top approach, and then this is the bottom approach. Okay, so then the CO pi bond will then break accordingly. Yeah. So because of this, in the process, right, racemic alkoxide intermediates, okay, will be produced, okay, because the geometry about the carbonyl carbon is trigonal planar, okay, allowing the cyanide nucleophile to approach it from the top and bottom plane with near equal probability. Okay, yep. And after protonation, I'm going to get a racemic product mixture. Yeah, so because I get both the enantiomers, so the plane polarized light will be rotated in both directions, and then eventually it will cancel out. Okay, so therefore the product mixture you get at the end of the day from the synthesis in the above steps is not able to rotate plane polarized light despite having a chiral carbon. Alright, so I hope this is clear enough. Most of the things you probably need to know here are actually coming out directly from the lecture notes. So yeah, so this represents some of the basic concepts you need to be aware of when you are dealing with this topic. Okay, so with that, we'll move on to question 2. Okay, so for question 2, you were told that in 1834, the French chemist Eugene Perregaux published his investigation into the action of heat on group 2 salts of carboxylic acids. So he noticed that the salt decomposed to give the metal carbonate and the carbonyl compounds. So this is some form of thermal decomposition. Okay, so it's thermal decomposition. So remember that for thermal decomposition, right, it is not the same as combustion. Oxygen is not involved. Yeah. So basically, the compounds, in general, they have huge anions, and then the action of heat might cause the anion to decompose to give you smaller organic compounds and maybe more stable and a smaller anion. Yeah. So such reactions tends to be entropy driven. Okay. Then when the reaction is carried out by heating 1:1 molar mixture of calcium adenoate and calcium metanoate, a mixture of 3 carbonyl compounds is being formed, all having MR less than 60. Okay, so you're supposed to suggest the structures of the 3 carbonyl compounds and then and the ratio in which they might be produced. Okay, and it will be good for you to explain why as well. Okay, so so before that, maybe we can try to understand how calcium ethanoate decomposed. Yeah, so the easiest way is really to color codes. Okay, so I'm going to show the ethanoates. Okay, so CH3, C double bond O, O minus. Okay, and then I'm going to show using another color, maybe in red. Okay, CH3, C double bond O, O minus. And then my calcium 2 plus, I'm going to write it in black. Okay, so this particular compound, when I apply heat to it, okay, you notice that I can get calcium carbonate and propanone. Okay, so if we just perform some sort of pattern recognition, okay, so maybe one of the ways where carbonate can be, I can get carbonate is like this. Okay, just going to put the dotted lines. Okay, so this is probably one way I can get the carbonates. Okay, and with that, I'm just going to draw out the carbonate first. Okay, so maybe I'm going to draw an O minus. Okay, a sigma bond, and then a C double bond O, O minus, and then I'm going to draw out the carbonate Ca2 plus. Okay, and then plus the propanone will then be like this, CH3, and then C double bond O, and then CH3. Okay, this is just one combination. You notice that I might be a little bit biased when I box up the portion in green. Okay, so now I'm going to erase this portion in green. I'm going to box up from another direction so you can see how is it different. Okay, so I'm just going to erase it very carefully, not to touch any of these bonds. Okay, have to be really careful. Okay, so now I'm going to use yellow. Okay, so I can box it up this way, like this. Okay, so this is one possibility. Another possibility, how I can get the calcium carbonate. Okay, so I'm going to draw it out. So O minus, and then okay, and C double bond O, O minus, and then this is calcium 2 plus, okay, and then CH3, okay, and then C double bond O, and then CH3. Yep. So there are 2 ways we can get the calcium carbonates and propanones. Okay, so right now, if I'm just going to expand it a little bit. Okay, so what I'm going to do now is I'm going to have a combination of calcium ethanoate and calcium methanoate. Okay, so I'm just going to write it down below. Okay, so it's the same thing, CH3, C double bond O, O minus. Okay, and then of course CH3, C double bond O, O minus, and then calcium 2 plus. Oh, sorry, I used the wrong ink. Okay, so this is calcium 2 plus. Okay, and then the other one is calcium methanoate. Okay, so I have a methanoate here. So methanoate. So calcium methanoate is the salts of methanoic acids. Okay, so I'm going to do the same thing. Okay, and then with calcium 2 plus. Okay, of course now I'm not going to showcase to you all the possible combination. Okay, because that will probably take up too much time. Yeah, but there is one thing you can say, you can definitely conclude for sure. Within the same salts, that means let's say calcium propanoate, right? I will definitely be able to get propanone out. I hope you will agree with me on that. And of course, calcium carbonate. Okay, and there are 2 ways to get propanones. Okay, so therefore I can conclude that the first product I'm going to get is propanone. And I'm probably not going to color code for you. I'm just going to write out normally. Okay, so propanone is one product I can get. Okay, so there are 2 ways I can get propanone. I just put a 2 over here. Right, and then within calcium metanoates, I can get methanol. Okay, over here. Okay, I'm just going to draw this out, methanol. Okay, and again, there are 2 ways I can get it. Okay, and of course, it is possible for them to crisscross. Okay, I hope you can agree with me on that. Okay, how are we going to crisscross? Okay, so we can have this combination. Okay, I'm just going to circle it. I hope is okay. We can this combination, all right, and of course this combination. Okay, so that's 2 ways. Okay, then alternatively, I'm going to use purple. We can have this combination and this combination. Okay, so that means I will be able to get ethanol in 4 ways. Okay, so in 4 ways. Yeah, so therefore the final product ratio, I would expect 1, 1, 2. Okay, so maybe I should erase all. Okay, so the final product ratio, right? I'll just write it on the over here. So it should be 1:1:2. Yeah, so I divide by 2 throughout. So divide by 2, divide by 2, divide by 2. Okay, so I hope this explanation allows you to understand why the product ratio is, in this case, is 1:2. Okay, so propanone, methanol, and ethanol. Right. Okay, then finally, for part B, suggest 2 chemical tests that could be used to distinguish the 3 carbonyl compounds, okay, from each other. You should state what you observe for each compound in each of the tests. Okay, so I'm supposed to use only 2 chemical tests. So let us remember this, only 2 chemical tests. Okay, so my suggestion is it will be easiest if we can tabulate our answer. Okay, because tabulating allows us to see, to make it easier for us to decide which combination represent the truth, or rather which combination allow us to help in distinguishing between them. Okay, so because we're supposed to use only 2 tests, we have to choose them in a relatively strategic way. Okay, so the first test that I would propose is Tollens reagents. Okay, so I will use Tollens reagents. So this is a silver mirror test. So I'm going to use Tollens reagents. Okay, if you want, you can just tabulate like this. Yeah, Tollens reagents. Okay, then for propanone, I will not observe silver mirror, so no silver mirror. Okay, but for methanol and ethanol, I will observe silver mirror. Okay, and then in this case, silver mirror. Right. Then the next test, I probably want to be a little bit strategic. Definitely, I won't be using things like 2,4-dinitrophenylhydrazine or even Fehling's reagent. Yeah, so I need a very specific test. So therefore, I will be choosing the iodoform test. So therefore, iodine warm in sodium hydroxide. Okay, so for the case of propanone, I will be able to get yellow PPT. Then for the other, for methanol, no yellow PPT or absence of yellow PPT. Okay, for ethanol also yellow PPT. Okay, so you notice that if I'm just going to simplify the whole matter, right? For Tollens reagents, it will be cross, thick, and then for iodoform test, it will be thick, cross, thick. Okay, so in that case, how are we going to distinguish between the 3 compounds? Okay, so I think first of all, right, based on this particular table, I'm sure you can tell that ethanol is the only chemicals that will give you a positive test with both Tollens reagent and iodine in sodium hydroxide. Okay, then for methanol, it only gives you a positive test with Tollens reagent, and then for propanone, it only gives you a positive test with iodine warm in sodium hydroxide. Yeah, so this table alone allows us to distinguish between all the three compounds despite only carrying out 2 tests. Yeah, so sometimes you need to be a little bit strategic when you plan out the test to be used to test for your unknown. I hope this will be a useful lesson for everyone. Yeah, so with this, I have come to the end of the review to in-class exercise 1 for topic 17 carbonyl compounds.